So thanks to Now and to the organizers for putting this together. I'm Colin Klein at ANU. I'm the chair of this, but I will turn it over as rapidly as possible. So we have two speakers today, Alex Maier from Vanderbilt, who's a Sloan Fellow and a Kavli Fellow at the U.S. National Academy of Sciences. He mostly studies visual perception, and he'll be talking to us today about giving an intro called Fechner's Dream. And then after that, we'll have Tom Carlson talking about brain decoding, pathways to progress. Tom is the head of the Computational Cognitive Neuroscience Lab at the University of Sydney. And does a lot of interesting stuff with brain imaging. We're talking about older body schema work before he came. So lots of stuff relevant to consciousness. So I take it the plan is we'll have Alex will talk, and then Tom, and then we'll come back and we'll sort of have questions and so on, and I'll moderate that part of it. So with that, I'll turn it over to Alex.
Yeah, thank you so much, Colin. I'm gonna try and share my screen. Does this work? For those of you on Zoom at least. Okay, great. Yeah, so thanks so much for the introduction, Colin. The way this came about was that Now sent me Tom's great paper about Fechner's inner psychophysics, and I think it reminded him of conversations that we had. And I threw together a bunch of slides about what we've been talking about, but I'm very nervous about that because I'm speaking completely out of my wheelhouse. In my day job, I'm a neurophysiologist, and today I will talk about Fechner and history and philosophy. And I see big names on here. Shout out to Randolph Blake and other ones. Please feel free to jump in and correct me, and call in you too at any point where I go off the rails. So what are we talking about? Well, I think that the big question that a lot of us are interested in is that as neuroscientists, we believe that there's a causal link between our brain activity and our conscious experience. But so far for neuroscience, it has not been possible to go the inverse route and to reduce our conscious experience to brain activity. Or if you would want to flip this arrow around, to come up with mathematical laws or laws of nature that we could explain brain activity and then how it gives rise to consciousness. And David Chalmers has termed this the heart problem. Of course, this goes all the way back to ancient Greek philosophers, the mind-body problem. But it humbles us neuroscientists that we seem to be far off. And indeed, there's a lot of people that think that this can never be solved. Well, I think that everybody who's speaking today seems to have a different opinion, and I'm happy to be in that club. So here's a quote from one of Colin's papers, and he wrote, "The heart problem is hard, not because it has no answer, but because we do not yet know what a satisfying answer could look like." So it means there's a way out. It means we can be optimistic, and we might one day actually solve the heart problem. And Tom says the very same thing in the paper that Now sent me that we're talking about today. Here's a quote, direct quote from this paper saying, "Many have wondered whether science is even up to the challenge. We side with those who have argued, more optimistically, that the field requires a shift in thinking for progress to continue." So what might this be? Tom goes on, one straightforward approach is to directly compare the structure of a psychological space to an activation space. And that is, of course, quite relevant to the representational similarity analysis and other work that Tom and others have done. It's also relevant to work that I know a lot of people that have joined this YouTube channel are interested in. There's different words around it, qualia structure, formalized phenomenology, some people have called it. It's part of, I think, a growing movement now with conferences and special issues about mathematical models of consciousness, with integrated information theory probably quite leading. But there's also, of course, artificial consciousness, and then this overlap with artificial intelligence and machine learning. So I just put here an older graph from one of Nao's papers, where he, in a way, makes the same proposal that if we can extract certain activity from the brain, we can abstract it. In this case, what integrated information theory predicts, that we can come up with causal structures, that there might be a direct relationship, a mathematically formalizable relationship that will allow us to transfer from these neural activities directly to our perception. And that reminds me of actually an even much older quote by one of my heroes, Henri Poincaré, who said that the aim of science is not things themselves, but the relations between things. Outside of those relations, basically nothing is knowable. So what I'm getting at here is that maybe the answer to the hard problem is that we come up with a relational but formalized, mathematically formalized way that we can translate between these very different domains. So what's there to object? Well, a lot of people would disagree. And so I want to go over that a little bit and then also really highlight Fechner's role in maybe getting a way out of there and proposing inner psychophysics as a way out of that. And then throw the ball over to Tom to talk about his proposal that we might have tools in our hand now that allow us to do that inner psychophysics. Those of you that I've lost at this point already, hang on, you might at least be interested in what I will call the dark side of Fechner. So I will reveal something about Fechner's work that has been hitherto unknown to the English-speaking world. Okay, so where does skepticism come from? A prominent person who was skeptical about us solving something like the hard problem was Émile Dubois-Reymond, who wrote a very famous book where he outlined big riddles that science didn't seem to be answering, and he thought science would never be able to answer. So he used that Latin phrase, ignoramus et ignorabimus, we don't know, we will never know. And one of the 7 riddles that he came up with, the 5th one, is the origin of simple sensations. So that's pretty much what we're trying to get there when we're trying to find out what consciousness, conscious experience, or phenomenology is. And so I want to contrast that with Karl Popper, who in a way set the stage for how a lot of us understand and see science by saying that theories have to be falsifiable. And so indeed, that is what a lot of people now use to distinguish between pseudoscience and science. But there's a limit to that, which is that there are some pieces of knowledge that most of us believe to be true, even without them being falsifiable. And so Kant would have called these a prioris. And so logic is one of these things, math, maybe, or maybe it's not derivable of logic, but there's certain truths that we also, without testing them empirically, most of us agree are probably true. Now, the point is that I'm getting at, that the hard problem may neither be unfalsifiable. I think there are on the horizon ways that we can maybe approach it in falsifiable ways, but there's also maybe not convincing enough arguments from philosophers that it's a priori an unanswerable problem. But that is a take that a lot of people have. And so one idea that has been proposed by Philip Joff is that this lies all the way back in the history of science, and he puts blame in Galileo's on Galileo's side by saying that Galileo was instrumental in making us think that the laws of nature are mathematical. So the short quote that you find on the internet, here's actually a much more beautiful one when you read his actual book, is that the book of nature is written in the language of mathematics. Well, I'd like to expand on that. And actually, I think that maybe a bigger harm was actually done by Isaac Newton and by Lavoisier, because they would take that science is not only mathematical in nature, but it is most and foremost quantitative. And so there's a distinction there, because you can propose mathematical models that are not necessarily quantitatively testable. String theory might be one of these, the Big Bang theory. But you can also, it's a question of what science is. And I put a few more people on there, such as Francis Bacon, who often got credited with coming up of the scientific method by making a strong case for observation and induction. And maybe even Descartes, who was the first one to really distinguish between mind and body in this way, might be part to blame as well. But I want to focus for now on this point that science has to be quantitative. Newton put it in this beautiful quote that he said, God created everything by number, weight, and measure. He actually took that directly from the Bible. And you can see the famous painting of Newton himself, how it might relate to biblical interpretations. So he was a very staunch proponent that if you can't measure it, it's not scientific. And so when it comes to perception, there seems to be a problem. And so you can still find quotes online today, such as our love cannot be measured. It just is. Sounds great. You cannot measure love by a scale of degrees. And of course, that is exactly where Fechner came in. So Fechner changed the understanding of a science of perception and therefore of consciousness from an a-quantitative to a quantitative one. So Fechner was the one that said, yes, we can bring the science of perception into the fold of science as a whole, even if you believe that science is quantitative, by making perception quantitative. And of course, the big trick that he came up with was to use thresholds. So most of us are familiar with absolute thresholds. That's what happens if you go to get a hearing test done. Somebody plays different tones, and at some point they're loud enough for you to hear, and you just indicate when it happens, and you repeat that, and eventually you find out how loud does the tone have to be before you hear it. But the genius stroke was to extend this thinking of thresholds also to stimuli that are far above thresholds. So sounds that you readily hear. And the exact same experiment is done. Only in this case, you're asking for when does your perception change? So you're not asking when do you start to perceive something, you're asking when does your perception take on a different form? And so instead of an absolute, you're now coming to a relative threshold, or the just noticeable difference, as it's still being called in psychophysics. And what that's, and I apologize for the dad jokes on the side, but what I want to get here is that he made perception countable. So we can start to count perception, and not only that, he made perception in a way binary. So if you look at this diagram right here, and for those of you who can't see it, I apologize. But basically what I'm getting at is that even as stimulus intensity gradually increases, your perception does not. So there are certain stimuli that change too little for you to notice the change. And then at some point you hit the threshold and your perception will change and you will notice a difference. So what that means is you're going from no change to a change. So it's a binary difference. And that allows us to get perception to numerosity. So instead of thinking of love as something that can't be measured, that's continuous from very little to very much, it seems to be discrete. It seems to go up in steps. And in fact, that is what Fechner did. And it allowed him to then come up with mathematical laws, the Weber-Fechner law that is still in use today. So if you measure these discrete steps in perception, if you use the numerosity, if you use these units that were now provided for perception researchers, these just noticeable differences, then you can find out that there's a relationship, a direct mathematical relationship between the nature of stimuli, the amplitude of stimuli, and your perception. It follows a logarithmic law. So great. That's maybe all we need. We want to translate from the physical world, from the body world to the mind world. Where's the problem? Well, there is a problem, which is that if you look at these laws, for example, these logarithmic laws, very often you find that they don't seem to tell us really much about the brain processes that have something to do with our conscious perception. Rather, they seem to happen upstream. So as one example right here, I just put a graph of dark adaptation that's very carefully measured here for a lot of subjects. And you see that there's a very characteristic curve, and it's not a continuous curve. And if you very carefully measure the cone and rod absorption answers, light absorption answers, you find that this curve basically follows exactly the curves that you find in the retina. So what I'm getting at here is that some of these psychophysical laws, as beautiful as they are, and as mathematical as they are, they might not tell us about the actual bridge locus, about the actual transfer of what happens in our brain from the neural activity to perception, since they might, in some cases at least, be limited to the input to the brain rather than the parts of the brain where the magic happens. And so Fechner, I believe, was actually quite well aware of that. And this is where I hope to fulfill my promise. So it turns out that Fechner wrote 2 books about psychophysics. And so the book that most people know is called the Psychophysics or Elements of Psychophysics. And in English, that's the only book you get, but that's only volume 1. It turns out there's a volume 2. And so that has never been translated to English. So I'm going to give you a translation of a part of it in the next slide. And so that's a translation that I tried to do together with Google Scholar, so take it with a grain of salt. So, but there's a whole other book, a whole volume 2. And in that book, Fechner talks about this problem that he kind of sees on the horizon, and he talks about his idea about inner psychophysics. And I can tell you, as a native German speaker, it's very hard to read. There's probably a reason why it never got translated. It's one of these books that in philosophy that I like to read in English because they make more sense to me when I read them in original German. So whole paragraphs that are just one sentence. But my take on what Fechner is trying to say and convey here is that he understands that there's a difference between sensation, so the processes that might happen in our sensory periphery, such as rods and cones absorbing light and answering to that. And he called that the Reizwirkung, or basically the effect of the stimulus. And he differentiates that from what we nowadays might call the neural correlate of consciousness, or the part of the brain, the bridge locus, if you will, where neural activity translates into consciousness. And he called that psychophysische Tätigkeit, or psychophysical activity. And so he understood that some of the laws from outer psychophysics, the psychophysics that we know, where we compare the sensation strength, the stimulus strength to the sensation strength, might be explainable with the effect of the sensory activity, with the Reizwirkung, as he called it. So here's a part from volume 2 of his Elemente der Psychophysik. It is the simplest and most natural assumption that the increases in the activities in the visual and auditory nerves by light and sound are proportional to the increases in the stimulus. So he's saying there that if you would measure the responses in the auditory nerve, they should follow psychophysical laws. And so he understood that probably that's not where perception is actually happening. And he gives an argument for that. So then he goes on and says, this would not suffice. And then he gives an argument that's quite surprising for the time. He says that because perception of the pitch of tones follows a corresponding law, one would have to think of the number of vibrations. And so I'm putting in here that's of the psychophysical movement. So you can think of that of neuronal activity as dependent on the number of vibrations of the stimulus, which is in fact unthinkable. So what he realized is that we can hear tones of much greater frequency in the kilohertz range, and neural activity would not be able to follow as fast. So he understood that there must be something happening beyond the sensory activity that seems to be closer to our perception. So Fechner, I think, basically realized that there might be this problem, the limitation to his discovery of psychophysics. And I just want to put this in context. When he wrote that in 1889, that was way before Hans Berger published his discovery of the EEG in 1924. So it's quite remarkable how much he already thought about brain activity here. And for those interested, I put the link to the German second volume of Elemente of Psychophysics there on my slide. So you're welcome to grab that and put that into Google Translate. So to summarize, so psychophysics in itself might have a limitation in terms of us getting to solve the hard problem. And Fechner suggested that we could get around that by doing inner psychophysics. And so his idea of inner psychophysics was that rather than measuring the sense, the sense response, basically the conscious percept to a stimulus of varying strength, we should measure brain activity. And his dream was that we could come up with mathematical laws, such as the psychophysical laws that we know, that would allow us then to take the brain activity, put in the numbers, and come out with the percept. And somebody who picked up on that quite early also is David Chalmers. So I found in one of his books that he proposed that also proposed that the way out of the hard problem may be that we can come up with these mathematical psychophysical laws of inner psychophysics that would help us to translate between the physical world and the conscious phenomenological world. And with that, I will throw the ball over to Tom.
Thank you, Alex. And I'd like to also thank all the organizers for bringing this together. So I'm going to, I will talk a little bit about Fechner's inner psychophysics, but I'll be better embedded in a much larger talk in which I'll talk about sort of how we can use machine learning methods to sort of make progress in consciousness research, but also embedded in that is like potential pitfalls, because it's a time where people are very excited about these methods and big data, but sometimes with that enthusiasm we can lose sight of kind of important things, and by not keeping these things in mind, it sort of can limit our progress. So a brief, studying consciousness in the human brain. I started out studying consciousness as a PhD student using psychophysical methods. I should give a tip of the hat to Randolph Blake. I saw him in the audience. He's one of my inspirations. So to study consciousness, we have lots of different sort of paradigms and methods. So, we have things like binocular rivalry, continuous flash suppression, masking. Now we get no report paradigms, and these could all help us sort of, using these paradigms, we can sort of distinguish, well, to use a quote from Blake's paper, one of Blake's papers, what can be perceived in the absence of awareness. And then we can also couple, if we want to know about consciousness in the human brain, we can couple that with all these wonderful technologies that are getting better and better every day. EEG, fMRI, MEG, single unit recordings, the list goes on and on. But when we're studying consciousness, often there's, at least in the early work, there's a very simple dichotomy, and that's exemplified in these two slides, where it's sort of looking at conscious versus unconscious. And what we can't get from that simple combination is, what's happening within these little colorful blobs. We want to know what's happening in these blobs, because that really dives into, talking about discussions of representational content, which is critical in, discussions of, consciousness. So the standard analytical techniques don't allow us to look at representational content. MVPA, or decoding, I'll use the term MVPA because it's a larger suite of tools. So what can these tools bring us to consciousness? So the first thing is they can actually bring us much more direct access to representational content. So here's one of the classic studies from 2005, Kamikanya and Tong, where they showed you could decode the orientation of a grating that is shown to an observer. But not only that, but you could even decode what orientation grating they're attending to in when there's two gratings simultaneously presenting. So you not only can decode the stimuli, but you can also decode sort of the perceptual sort of state of the observer. And we can even extend beyond this into more sophisticated sort of ways of looking at brain data. And this is largely championed by Nikos, where you can sort of reconstruct representations in the brain. I'm hoping most of you are sort of familiar with this work, but the idea with RSA is basically you measure differences in brain activity in a large number of stimuli, and then you're going to get a whole bunch of little tiny distances between all these possible pairwise combinations. And from that, you get this sort of larger geometrical representation of stimuli in the brain. And that's exemplified here. So the red and the blue is basically encoding of the little distances. And over there, the pictorial is sort of flattening this space. And now distance is represented. The difference in brain activation is represented in distance in the figure. So faces elicit very similar patterns of activation. The face and a banana elicit very different patterns of activation in human IT. And from that, you can get some nice intuitions about what IT cares about. And here you can see there's pretty clear division between animate and inanimate objects. So these are wonderful tools. for studying consciousness. And when we apply them, we can, ask a lot of different questions. So one study that I did with Sue Wardle, very simple. We took all these sort of very kind of simple and very complex patterns of gradings. And then we had people make similarity judgments. So they just see two of these images on the screen and they say how similar they thought those to be. So it's just a pure abstract perceptual judgment. Then we can go ahead and we can take and put the subject in the scanner or a new set of subjects in the scanner and show all these stimuli, reconstruct the similarity matrix. And then what we can do is we can compare our perceptual similarity matrix. So this is the model based on people's just abstract judgments of their similarity. And we can compare that to neural activity that we measured using MEG. And here we can see starting about 60 milliseconds, we have a good fit with what we call a retinal envelope model. That's not important. But about the same time, this gray line goes up, and that's the link between our perceptual ratings and the neural activity as measured by MEG. So using these methods, we can make kind of nice links between perception and brain activity. Now, what I want to bring to you today a little bit is, like I said, there's a lot of excitement about these methods, but there's a lot of thought that needs to be going into when we apply these methods. So these methods are a basis for opportunity to sort of expand our understanding of the neural spaces of consciousness. But our progress is going to be limited if we don't really think carefully about what we're doing. So what I'm going to talk about for the next few minutes is a few of these pitfalls that we've sort of thought about and identified over the course of many years. And there's a paper out there that I'll give you the citation at the end. Okay, so the first pitfall to think about is what is the source of decodable information? All right, so we go into, we'll go back to this Kamikanya and Tong experiment. And if you really just sort of think back, what they did was decoded the gradings that people were looking at or attending to. And if you think about it abstractly, that's not actually that exciting because we've known for decades that basically in V1, there are orientation to neurons. So, the full expectation is we should be able to extract this information out of activity from V1. What was really exciting about this particular study was fMRI voxels are about 3 millimeters, and orientation columns are much smaller than that, less than 1 millimeter. So if we take an fMRI voxel, what we're going to see is a whole bunch of orientation columns are being mixed together, and you would expect that all sort of wash out on average. And if that washes out on average, then there's no reason we should be able to go from an fMRI signal to what the perceiver is looking at. And sitting in between is sort of the problem. And that's this black box of machine learning. These methods are extremely sensitive and they can pick up on all different types of information, but we don't know what information they're actually using. And if we really want to sort of make progress on, sort of mechanistic explanations, we want to know exactly the information that these classifiers are using to decode what people are seeing. Now, I'm not going to unpack these at all, but there's actually 3 ideas out there. The original one put out by Kamikanya and Tong is the idea of hyperacuity. And that basically is that there's going to be little teeny tiny biases in these voxels. And the super sensitivity of machine learning is able to pick up these tiny biases and from that extract the orientation of the gradient. The second one is called a biased map account. And that's just within locations of the retinotopic cortex, there's different proportions of neurons to the different orientations. And the most well-known is what they call the radial bias. And finally, another one that we identified, or that I identified in 2014, was actually, interestingly, there's sort of an edge artifact in the stimulus that potentially the classifier could be used to exploit to decode orientation information. Now, obviously, I have my favorite among these theories, and I'm not going to go into them. But the point that I really want to make here is that all of these are different theories about where that information is coming from. But if we don't know what the source of the information is, so how do we take the next step into sort of making our mechanistic explanations about what's sort of happening with a particular process? So we really have to think carefully about what is the source of decodable information. So this black box is really quite problematic. As I said, it creates this ambiguity for mechanistic explanations, but it also makes us extremely vulnerable to confounding factors. I'll highlight an example. This was informal, never a published study, but somebody told me once that they did an MVPA study where they used a pseudo-randomized sequence in fMRI, and there was just more of one condition at the beginning of the run and more of another condition at the end of the run. And basically, the classifier was using the drift, the X-drift gradient on the fMRI signal to decode, the stimuli. So in that case, it had nothing to do with what people were observing. It was just, literally fMRI machine noise that was being decoded. There's also vulnerability to confounding factors. So this one is a paper that sort of shocked, I think, a lot of people quite a few years ago, where they showed that you could decode, kind of in limit fashion, you could decode somebody's decision 10 seconds before that decision entered awareness. And I think most of the research community was like, what? That's insane. I can change my mind 50 times in 10 seconds. How could you possibly read my mind 10 seconds before I made that decision? And it turns out, research following up on that basically linked that to kind of psychological biases and sequential decision making. All right. So the first thing we want to think about when we're sort of applying these methods is, what is the source of decodable information? We should be confident about that as we're making our explanations. Second thing we need to think about is this information accessible? So this is a study by Mark Williams a long time ago. And basically they're showing 3 different categories of stimuli to observers, and they're trying to decode which stimuli the observers were viewing. And this is done in sort of a masking paradigm. So brief presentation followed by a mask. So subjects weren't perfect at doing the task. And what this study showed was that in LO, they could only decode the stimuli that were reported correctly. So if the person was actually conscious of the stimuli, then they could decode. But in V1, they could decode the stimuli regardless of whether or not they could correctly report the stimulus. So what that tells you is that activity in V1 isn't really linked to the conscious experience, because it's always there, regardless of whether or not the observer experiences this. So the implication of the study is basically that V1 is representing information that's inaccessible. And this gets to something I call the egocentric neuroscientist, at least when I talk about decoding, is that a lot of people jump in with a lot of enthusiasm, but they don't realize what you can decode from the brain is not necessarily something information that the brain has access to. Another good example is, you can decode what somebody is looking at from the retina. If we, did a scan of the retina, we could tell exactly what that person is looking at, but we don't. Our brain doesn't have direct access to the retinal information. So we have to think, when we're doing decoding, we have to think more from the perspective of what information is accessible to the brain. Here's another one that my friend George Alvarez actually raised to me with regard to one of my studies, which I'll talk about later, but issues of scale. And for this one, I think about something like global workspace. But in this original, Kriegerstort study, he produced sort of this beautiful sort of map of the geometric representation of objects in human IT. I should also note, Rusbeth-Chiani had a paper before this that was even more bigger, and they had thousands of stimuli from the primate IT that was included in Nikos' study. But when you step back and think about it, when Nikos is doing his decoding and reconstruction of the representation, he's using all of inferior temporal cortex. And sort of the assumption of, from a accessibility perspective is there's a neuron or brain area that has access to all of the activity in ITC. And that seems highly implausible. How could a single neuron be monitoring all of the activity across inferior temporal cortex? So we also have to think about these sort of issues of scale. Can we access that information across such broad areas of the brain, large scale parts of the cortex? Okay, so part two is thinking about, is this information accessible to the brain? And this final bit I'll talk about is readout, and this sort of links back to Fechner and his inner psychophysics. So the last thing we need to think about, and it relates to the accessibility, is actually how information is being read out from a representation. So readout is, it's surprisingly not discussed that much when we talk about sort of findings in the cognitive neuroscience literature. Often it's sort of that we take that big first step and say, is this area representing Y, or is this area representing X? If we want to take like the face area, is the face area sensitive to orientation? And then we just stop there. We go, okay, well, because the face area is sensitive to gender, for example, we just assume that the brain accesses that gender information from the fusiform face area. But we don't know that. We just know that it's being represented. And one way we can get some clarity on this is by actually sort of thinking about how information is read out from different brain areas. So this issue was raised by Reiki in the 90s. There's a really beautiful paper by DeWitt in 2016 talking about information theory in the brain. And we talked about it a little bit in the citation I'll give you in a little while. At least DeWitt basically said that one of the things that sort of they use it as a stand-in for biological plausibility is linear discriminability. So if there's information or representation that's discriminable by a linear classifier, then it should be read out, able to be read out by the brain. And I think this is exemplified. This is a beautiful paper also by Carlson and Cox, where I think in a way they turned the field of object recognition upside down by saying, we don't need to think about all these sort of stages of object recognition. Basically, all we have to think about is how we go from a bad representational space on the retina to a good representational space in IT. And the whole ventral stream, its goal is basically going from bad space to good space. And into Carlo and Cox's terms, good space basically means linear separability. So here is another case where there's the stand-in of linear separability is basically once it's linearly acceptable, then it's the area that the information is formatted in a way that the brain can use it. And here, and this was part of the argument of the paper that Alex mentioned, is we need this sort of shifting frame of reference that I've talked about previous, is we have to think of the brain as its own decoder. We really have to think about how the brain pulls out information from brain representation. So again, this is sort of the egocentric neuroscientist where we're sitting in our lab, we're looking at what information can be decoded from different areas, inferior parietal cortex, V1, inferior temporal cortex, and we're just sort of putting things into two bins, whether or not we can decode information. But what's really important is whether the brain can decode information from a representation. And this is a quote from DeWitt's paper that I particularly like. One cannot simply measure a physical property, the flow of electrons to wire, the firing of a neuron, or pattern of activity measured with fMRI, and assume that we've measured information. Rather, we have to construct a model of how that activity can be used by the receiver. So if we really want a strong model, we have to also talk about how the receiver can take up that information. So we can go, we can do this, and I'll show you in a second how we did it. But what we want to do is go from a representational space, like something that we can, we can get from Nikos methods to an actual behavior. And this is where it links up to inner psychophysics. How do we map brain activity to a behavior? So we did this using a very simple model. And I emphasize this is a very simple model, and there's a lot of issues and holes with it. But I think it's sort of important that we actually sort of put that model out there. We can say, this is how you go from activation space in the brain to a behavior. And what we did was pretty simple. We took this really complex activation space, actually the same data that Nico used. Nico shared that data with us. And then we said, okay, we want to build a readout model from the brain that separates animate from inanimate objects. Because in Nico's data, there's this sort of beautiful distinction between the two. And then what we did was basically say, okay, we're going to take this activation space and project it onto a decision axis. So each one of these stimuli is going to sort of project onto this axis. There's going to be a little bit of noise. We use some optimal decision boundary. And what we'll propose is basically the brain uses this as a readout model for making judgments of animacy. And when we did that, we found that indeed the model worked outstanding for actually predicting whether or not people were choosing animate or inanimate, but also how long it took them to respond. So when things are very close to this decision boundary, we expect it to be a harder judgment than if they're far away. So we can also make a reaction time decision prediction from this sort of mapping here. And what we found is for reaction times, we can get a very good fit from our model to reaction times for these choice judgments. Strangely enough, and we still haven't figured that one out, it only works for animate objects, not inanimate objects. But we also have this sort of nice dissociation that it really sort of works only in IT, but not in early visual cortex. So it's not something about the complexity of spaces, because things get sort of strange when you have really high dimensional spaces. Also, the information becomes available that normally wouldn't. But I won't go and touch into that. So this is your sort of inner psychophysics, and we're taking a brain model, a brain activation space model, and we're going from that to a direct prediction of behavior. Now, as I said, I think, I was very excited about this model. I still like this model quite a bit. But I'm also, quick to say there are all sorts of problems with this model. So there's good things. The good thing is we get this mapping from brain to behavior, going from activation space to reaction times. It's good it also links psychological models decision making to activation space. So if anybody's done any work in decision making, you'll see these types of models, these not activation models, but these sort of models are used in decision making all the time. But there are bad things. It doesn't work for inanimate objects. Still can't figure that out. Bad. We also, our implementation violates the scale thing that I brought up earlier. So we're trying to make, a decision based on all the activity in inferior temporal cortex, and that would, that assumption there would be whatever readout is happening, it would have access to all the activity in inferior temporal cortex. And that seems highly impossible. And it's bad and only works for two alternative force choice behavior. That's not very natural. When we think about object recognition, at least, we sort of look out in the world and we see a bike. We don't, sort of parse the world. It's like animate, inanimate, okay, mode of transportation, not mode of transportation, car, not a car. So it doesn't work for that. So there's these issues as well. But I say it's good because there's lots of space for young people to do better in making better readout models. Okay, so to quickly sum, I think I'm doing okay for time. I think it's an exciting time, and these methods are maturing, that we have these sort of methods, MBPA, that provide an opportunity for progress. We sort of argue people shouldn't get too excited. We should carry these sort of considerations in the background. Maybe they don't completely hold you back, like in the case of readout model, we're violating one of these considerations, but at least it's a start. And then we talked through several of these different considerations, thinking about the source of decodable information, asking, is that source of information accessible to the mind and brain? That's critical. And how this information might be read out, that's critical as well. So really this comes down to sort of, when you're doing your research, you're asking questions like, how good is your data in theory? If you have a theory, but it can't handle it, it has scale issues, doesn't talk about how information is read out, you're not thinking about your source of decodable information or accessibility, then there's more room for future improvement. All right, I'll put a cap on it there. I'll put the Twitter address. I don't tweet that much, but we do tweet our papers. And here's all the people that work with us on this. This is an adaptation from the material of a paper I worked with Brendan Ritchie, who is really one of the main drivers of the inner psychophysics work. Colin, your host, Aaron Goddard and David Kaplan, and I also talked a little bit about one of the papers I did with Sue. And then I will leave it there. I also acknowledge your funding body, the ARC. And thank you all.
All right, so thanks both to Alex and to Tom. I guess my job now is to figure out how we're going to run the questions. If people are familiar with the raise hand function, I can definitely see that. Or you can add things in the chat. There's already a vigorous discussion going on in the chat. I don't want to try to recap that, but very interesting stuff about consciousness generally and also about this stuff in particular. So does anyone want to kick us off with a question?
Okay, if nobody does, then let me start. Is that all right? So I think what Tom, you said about, and also Alex, both of you probably raised the issue of what can this type of the decoding of psychophysics is actually revealing in the end, right? And my sense or my argument for several years is that as long as you rely on the one single kind of decision or some kind of labeling, simple labeling of seeing or not seeing or something like that, then you end up in basically finding the mechanism that correlates with that only. And that's very different from how we see the world in any form. So rather than going into directly what information, what representation can we decode or access or something like that, I think the one step more sort of the promising kind of approach is to explore the path to get to the sort of the how people are actually feeling, maybe expanding or exploiting more of the richness of the similarity rating type approach to try to really characterize what it means, meaning for the people to see red kind of stuff. So this may be more of the probably question or a comment to Tom, whether you are satisfied with decoding or classifying the reaction time, or do you want to go beyond that? Do you want to comment?
I think it's a great question. I wanted to relate it to some of those principles, like as soon as you try to measure it, you're sort of impacting it. Like what you're saying is like, if you try to measure consciousness using some method, then you're sort of defining consciousness implicitly through that definition. One thing your comment did make me think about, and I think you're right, and like, is there things that we can do better with similarity spaces? And one method coming from Martin Haberts, who's now in Germany, I think is really good, is he has this odd man out paradigm, where he just shows you 3 random objects and you say which one doesn't belong, but you don't tell them why. And I think it's a really nice paradigm because it's unconstrained. So, with any given set of three, you might use different criteria to say why they're different. And from that, I think you can get to a much richer, build up a much richer representation of a space, as opposed to sort of directly asking them questions like, are these similar in form, or are these similar in texture, or are these similar conceptually? I think in Martin's first pass, that was like this huge big data thing. He found like he was able to sort of get a really nice, big, rich, reconstruct a very rich representational space of objects that included, things that maybe people, weren't really thinking about that much. So I guess in a way, I would say like, maybe the way to kind of push forward, at least with similarity spaces, is kind of do exactly what you say now, is to not ask people such direct questions and just let them minds wander and sort of find those different dimensions and let those dimensions pop out of the data.
Okay. I'll let others ask questions. Or maybe
Sure.
Colin. Yeah.
Oh, well, I'll keep us going forever if you want, but we have a question from Steve Carey. Did you want to read it out loud, or do you want me to, if he appears?
Sure, I'm happy to. I feel hopelessly out of my depth here, but I'm not quite understanding what the explanatory power could be. However good the machine learning project gets, doesn't it just give us a finer and finer grained account of neural correlates of consciousness without explaining consciousness? What's the explanatory power?
I'll quickly try to fill that one. I think you're right, in that it is just a finer grained account, but I think that granularity is important. So if I flick back to like one of my early slides, when we're talking about, we'll just generically pick this study right here. You compare, yes, I saw it, no, I did not see it. And you get all these different blobs, and then they're all sort of entered into the sort of matrix of consciousness. But if we're asking, in this one, maybe they're trying to say something about conscious representation of faces. If we want to talk about the conscious representation of faces, we want to know which one of these blobs is encoding that kind of fine-grained granularity of faces. So in one of these blobs, this might be, let's call it the attention blob. This might be the working memory blob. But it's this blob right here that's encoding, faces tilted to the left, faces tilted to the right, faces that are male and female. And for that, I would argue, it's this blob here, or that face blob, that is the sort of source of conscious sort of information. So I think that distinction between looking at content is helpful, but you're also right in that like it doesn't necessarily solve one of those sort of bigger problems of consciousness or identifying consciousness.
If I could jump in on here, I'll play devil's advocate for representations as well. Like I think you can actually say it's possible to say something slightly stronger, right? So if you've got, there are people who are sometimes called representationalists about consciousness. And whether you find this, many people find this unsatisfying, but the idea is that we're conscious of the world because we have a certain kind of representation of it. So it's not just a brute fact, but it's something like, you've got a certain kind of map, the right kind of map in your head or whatever. Now, if you think that, then just finding this is what I always took the upshot of some of this stuff to be, is just finding blobs that activate. That doesn't tell you very much at all, but showing what you're representing shows you quite a lot. So that's actually, because that's actually the ingredient. That may not get you all the way there, but that's the thing that's at least the necessary ingredient of consciousness. One way to think about it, I often think in these kinds of analogies, is if I'm just trying to explain how a computer works, right? And I want to know like why my computer is running Word rather than LaTeX. Looking at the processor and the memory are all just going to be doing stuff. Like it's not going to be a huge difference between running one program and running another. What makes the difference is the representations of the program and the data and so on that are going through it. Like, that's really where I'm going to get the interesting explanation. So I think at least moving from univariate analysis to decoding, I would say for consciousness was supposed to at least be getting you closer to the things that are really going to make the difference. Although in some sense, you know, it's true that if you go down, in some sense, it's all neurons firing one way or the other, but it's at least giving you like kind of a better theoretical look at, you know, a theoretically more useful look at what those firing neurons are doing. That's the idea. And then there's the question is whether you're actually getting representations or something else, which is most of the pitfalls part of the talk.
And if I can piggyback on that real quick. So I think when it comes to explanatory power, when we think back to what Fechner has done, I think it's that he went beyond a Pearson R value. There's not just a correlation. And I think that's a problem that we're dealing with in the neuroscience of consciousness at this point. That's where a lot of people feel the NCC approach is stuck, and maybe even machine learning. So Tom and I had a little bit of a pre-discussion of this. And so there was a lot about, is this still correlational? Because what Fechner did is he gave us a logarithmic equation. So that's almost like Newtonian physics. At that point, we're dealing with something that seems, again, like the book of nature is written the law of in the language of mathematics. When we have a simple equation, there's something in us that feels like that's an explanation. That seems to be closer to what's ontologically out there. And whereas with a correlation, we understand there's confounders, there's all kinds of the Simpsons paradox, there's all kinds of problems that keep us from really understanding causal relationships with correlations. And so what I see in Tom's talk and in his paper is that he's thinking, especially when he said when it comes to readout, he's thinking that is there a way that we can move beyond correlation? Is there another mathematically formalized way that we can take the neural data and then bring it closer to what our experience is? And I do see hints of that. I do see that there's hints of that. And anybody who's interested in this, I encourage you to read now his papers, to go and find his YouTube videos and his talks, and also Giulio Tononi's, other people, Johannes Kleiner and so on, because there's a lot of people thinking alike at this point, and I see Tom very much in the same vein, which is to move away from something that is correlational and simple to something that seems to be multidimensional, that seems to be maybe more based on spaces, geometry, rather than a very simple linear relationship. And I think that there's like a hunch out there that people understand that might be what's heading us in the right direction, that there could be mathematical formulas, but they're going to be more than just a Pearson's correlation coefficient.
Yeah, great.
We've got a hand from Camilo Lewadinsky.
Yes, hi. Can you hear me?
Yep.
I have a question perhaps for both the speakers, but when we're talking about representations, and I think Thomas gave an example of the retina containing some implicit information about, for example, faces that it's not necessarily accessible to, let's say, the LGN or the rest of the brain. But let me see if I get this correctly. Do you think then that the representational content is a function not only of the activity of a specific region, but the specific way that this information is used by downstream areas, right? So if I had, for example, an LGN that was a very high dimensional space where you just feed the retina and then an organism, all that it does is go away or forward from faces, would that then mean that the retina is representing face information?
Yeah, maybe sorry.
Go ahead, Alex.
Yes. So again, I'm going to keep on marching in the same direction. So I feel that there are theoretical answers on there. And I'm a convert, again, when it comes to the work of Giulio Tononi and others have pushed forward, because it does seem to provide answers to some of these questions, right? So it solves the problem of who's reading out. It solves the problem of which part of the brain, the granularity problem, or the problem of scale that Tom discussed and that Paul Martin also had great comments on. And because IIT says exactly it should be these types of activity or these causal actions, and only those will translate to your experience. And the beauty of this theory is that it's not only falsifiable, it doesn't only provide qualitative predictions, as some other theories do, but quantitative ones. So there's a Python code available that you can throw in your neural data and you can run it and you can get quantitative answers to some of these questions and some of these predictions. So the LGN, for example, if we have all of the data of the LGN and we should throw it in there and then we look at other visual areas, we should find that there are differences in these scalars that that are measured in terms of, not to get too much into the weeds here, but in terms of the intrinsic information that's flowing, or the causal interactions that are happening between neurostructures. Does this make sense? Maybe I went in the wrong direction.
Now, did you want to, oh, sorry, Tom, if you had something now, I feel like you also wanted to fight about representation. Maybe
yeah, I always have a problem with the term representation. And so, today it's great that, we have people like Colin from philosophy side. I really don't, I study, I read this, representation or something like that within the Stanford Encyclopedia Dictionary for, philosophy and so on. But I never understand why it's something to do with consciousness, actually. Because when we, experience something, either opening my eyes or, in the dream or hallucination or something like that, we are experiencing that. And only in subset of our cases where we are seeing something veridical corresponding to what we are perceiving with respect to most likely thing out there in the world, then only then this concept of representation kind of makes sense. But representation should be happening at many multiple areas of the brain, and also, as Camilo said, like if it's represented in the retina or sphericolliculus, which clearly we don't have any access to, or no similarity in terms of quality, then what kind of benefit do we have with thinking about even representation? I think it's just misleading. I mean, it may be useful to analyze the data from a third person point of view of the neurophysiologist, with the primary kind of motivation to find what is the transformation of information and so on. But I really don't know whether it does any good to understanding consciousness and how it's supported by the physical things like a brain.
Well, I feel like it does have some value. Like when we're talking about like retina LGN B1, well, this is where it gets a little tricky with the philosophers, because and I think we actually wrote in our paper this way, is like, what is representation? Representation is something that's being used. But I think maybe we can just more easily divide it into sort of representations that are being used and representations that are not being used by the brain. So you'd say the retina is a representation that's probably not being used for conscious experience, or highly unlikely. But if we want to sort of get to how conscious experience, what is the format of conscious experience, then that is another representation that we can map back to, link back to the brain in kind of classic NCC fashion, using things like the representational similarity analysis. So you could generate, I'll just do like, I'm sorry, I have to move some things around, but you can generate models. Like this is a V1 model using HMAX to stand in. And you can correlate, that to neural data and say, how well does that sort of explain the neural data? But you can also take, if we had an fMRI study where, and I think they do this quite a bit, they do it, they'll do the data from V1, V2, all the way up through IT. And then you compare all of those areas to perceptual ratings, and you're able to see that IT's representation much more closely maps on to perceptual ratings than the V1 representation. So I think you can use these methods to sort of adjudicate, what role these different areas have in consciousness. But I also should say, like, I don't necessarily believe there's some sort of binary role where they're participating or not participating. I think V1 does contribute to, consciousness. So maybe you sort of have to have some graded view of representation as well.
Could I jump in on this as well. And also there's a good question. Aniko, I didn't know if Aniko Kustor had a good question. I'm not sure if that you wanted to ask that or if you mind if I just answer it, because I think it's really important. But if you want to jump in, go ahead.
Yeah, no, I go ahead. You can just read it. I think that's,
well, so I think that's this really good question about the relationship between representation and illusions. And what does an illusory experience represent, which I think is a great question. And I just want to, the view from philosophy, just to give you a kind of package of views. So part of the problem is if you go and try to read the SEP on representation, it's a huge, gigantic swamp. A lot of what philosophers are trying to do when they talk about representation is not anything you care about. And to be honest, not anything I care about. Like, I find it often quite a tedious literature. But I think there are really two things going on here, and they're going on separately. One is a very kind of foundations of cognitive science sort of idea. So this is look, we understand the brain on the model of a computer. What does a computer do? It's defined in terms of operations over representations. That's a very useful explanatory schema. You can quibble a lot about what the representations are and what the operations are, but unless you want to go be like a behaviorist or a madcap Gibsonian or something, this is the line, you care about representations as much as anyone else. That doesn't say anything about consciousness, but it kind of gets representations in the door. And then the other trend, and this is I think there's an old paper by Gil Harmon who really kicked this off. And I think Steve's question about what is the definition of representation, that's unfortunately part of the problem. I'll say something about that, but just in terms of illusions. So the idea is, you start off with this idea that you can have things which represent things that aren't there. So a picture of a unicorn in some sense represents a unicorn, even though there aren't unicorns and have never been unicorns. And that's kind of cool. You can also represent things that, used to be here but aren't anymore, like with a photograph. And one of the things that representations in the brain do, like memories, represent things in that sense. So then the idea is supposed to be something like, well, when we represent something, really what we're aware of is the object of that representation. So if I hallucinate a unicorn, I'm aware of, in some sense, the unicorn, not the representation itself. But it gives you this framework that's supposed to be parallel with thinking about pictures or photographs or whatever. So the idea there is that what you're conscious of is the object of a representation. What brains do is traffic a lot in representations. And so then all you need to do is kind of find, since we're clearly not aware of all the objects of all the representations we have, we've just got to find the right one. So maybe if you've got a global workspace theory or something, maybe the right one is the one that gets into the global workspace, or it gets blessed by frontal cortex, or whatever. That's an important detail. But it's supposed to be, I think, Steve, part of this is trading on two different senses of representation that everyone wants for them to come together. One is this that it's a kind of structured thing that you can work on that's supposed to point to an object, even in the absence of the object being there. And the other is that it's got this kind of structure so that you can do computational stuff with it. But then a lot of the worry in philosophy is about, how to make those true. I don't know, I'm going to a reading group after this for a particularly long and tedious book on representation. So there's a lot of infighting on that. But I think the idea is the quick version is representation is supposed to have some relationship to the general project of cognitive science. And that if you think you can understand consciousness in terms of this relationship that representations bear to their objects, then the hope is that you can take these slightly less mysterious things and reduce the more mysterious things down to them. I'm giving you this package that used to be more popular. I think it's probably less popular these days, but that's the kind of, so you can feel free to jump in too, Steve. I'm just sort of, I'm really about the,
Somebody asked an interesting question about now. Aniko asked a relationship between representations and illusions. That's not like a unicorn, where it doesn't matter whether the unicorn really corresponds to something in the real world or not. But when we are deceived by the way that we typically understand the world to see something in a way that actually it isn't, we see shading because our mind is making an assumption about where the light source is. Can we imagine that that would be represented somehow in neurons, or is that more kind of a less neuron-specific activity of the brain? I don't know.
I mean, I would assume, yeah, although some of there's a problem that I give my students. I think there are two things, and one, I wanted to get Tom to say something because I'm technically only the chair. But one interesting thought experiment about representations when I teach this stuff to students, I say, look, we know that when the image goes into the retina, it's upside down. Where does it get flipped back over? And and sometimes I remember being young and being really concerned about this. But the idea is something like, it doesn't matter whether it's right side up in the brain at all, or even if it doesn't need to be a little image in there. What matters is that, heads are represented as the top and feet are represented at the bottom. And it doesn't really matter how you do that. You don't need space to represent space or time to represent time or anything like that.
Wait. But that's something that I have some issue with.
Yeah.
Because there is an very rare but highly reliable kind of reports in a patient who has some kind of particular lesion in the brain. Sometimes it's a parietal and sometimes cerebellum and so on, who reports the inverted vision or rotated vision.
Okay.
So there is, I think when there is a conscious experience of this form, in this particular way, that the way we are seeing is this this way of spatial structure has to be supported by the spatial structure of the thing that's happening inside the brain that is directly sort of supporting this experience. And here I am less, I can kind of see the sort of correspondence of my way of saying the supported or corresponding probably corresponds to what you are saying as a representing probably, like also Thomas representing. But leaving aside, coming back to this space issue of the consciousness, there is a clear reason why we are experiencing things like this way, and if it's impaired, we don't necessarily experience the world as such. So, that's some detail, but I think it's an important thing to realize.
I think there are two things there,
Okay.
But also to jump to Tom. So just one thing, the kind of thing I have in mind with representations. So if you have an iPhone, sometimes when you try to upload your pictures to Instagram, they're rotated 90 degrees. And that's because there's a bit that Apple cares about more than some websites do, right? So it tells you, which rotation is in. It's literally, you change a bit and the representation of it rotates 90 degrees. It doesn't matter where those things are on the platters of your hard drive or anything like that. So there's all kinds of schema for representing space. But one thing because I'm curious about this, and since Tom's here, one place that seems like it would be a really interesting source of data is decodability on error trials. So do you know stuff where people say, they make mistakes and you can decode the mistaken representation rather than what was actually there? Because that seems to be getting at, again, both not just the seen and not seen, but also the kind of, what people are willing to report.
Yeah, I feel like I've encountered it through discussions, but I can't pull a citation. I know the big issue is it's just really hard to get people to make errors. I'm trying to think, Alex Wolgar was trying to do this. We had long chats about how to get the errors, but I feel like there definitely seems, in my mind, there are definitely studies which show that they show that they make the same errors that you see in the representation. I can't pull it. I can't think of it at the moment. I think Arash Afra said some of the stuff where they're perturbing activity in FFA and getting people to make errors, and similar with Shadlin and Newsom. And they sort of push activity around and force the monkey to make the mistake they want them to. But I can't put my finger on anything where they've done like an actual analysis of errors. One thing that now mentioned though that I wanted to can't cross my mind, like, hey, do we have anybody that's done like the prism, trained themselves with the prism glasses? Because I believe if you wear the prism glasses for a few days, you get used to working around in the environment. But I thought also qualitatively the world flips.
It does
Yeah,
not.
but that's a bit controversial, right? I mean,
Yeah.
Okay. Yeah, I don't have cited data for it. I always wanted to do it, but I just didn't have 3 days off.
I actually
Yeah.
have a paper from about 10 or 15 years ago that's got trying to review a bunch of the evidence on this. This is another one where if you go back to Kohler and actually read the original, it's much more ambiguous. And also, like, part of the problem with this data is that, or these experiments, is that they're so onerous that basically it's always the experimenters. So there's some more clever recent ones. There's a Japanese group that did one, I know, and there are a couple other ones where they're trying to do like shape from shading and things that, because otherwise it's very hard to like get people to say like, well, I can read it and I can interact with it, but it still looks upside down, is often just a weird kind of report to make. But yeah, I mean, I don't know. Now, do you know anything? I haven't looked at that literature in like a long time now, so I don't know.
Me neither. But what I know is that at the level of the animal studies, for example, prism experiment has been done in a barn owl and so on. And what they found is, this is the knowledge I learned around 2000 or 2005, so it's quite rusty. But they do observe some kind of new sprouting of the synapses in visual cortex and so on. And then when this kind of thing happens, then the barn owl also starts to adapt to this change of the visual experience induced by the prism. And then after several months, and then when they wear the prism again, they can adapt really quickly. But they can also adapt to the previous situation as well. And that's also correlated with the trace of the remaining new synapses formed by this new experience. So I think this case of inverted vision using the glass is a bit controversial, but I can imagine that could work if our human brain are reorganizing it in some way, and then that supports our experience of this non-inverted version. But as you say, Colin, I think it's really fascinating kind of replication project, in fact, in a large scale, if possible, and then do very interesting kind of experience sampling in many ways, because behavior itself is really deceiving, right?
Yeah, the original Kohler, they had them like fencing and like riding their bikes around, and like it's really kind of, I feel like it's all things that you couldn't get past an ethics committee, but would be super fun to try. So, Tom, did you want to?
Oh, I was to say, the description actually feels like when you move to a country and you drive on the other side of the road. Like, it's super painful for a week or two, and then you sort of get the hang of it, and then after time, it's like riding a bike. But the same thing happens when you go back to the country where they drive on the other side of the road. Like, it's painful, but it's just painful for like an hour, and then you're back into right side of the road or left side of the road. Maybe we can get something past ethics about driving on the wrong side of the road.
Yeah, that kind of cognitive level of the change is probably faster than the experiential or qualia level kind of change, like so drastic, like inverted vision, I think.
The one thing I also, if I recall correctly from some of this, what's interesting, and I think like this is, if you've kind of a modularist view, is that certain things came online fairly quickly, but you had reports, I think again, this is in Kohler, of people saying, look, I can walk around fine, but I still can't read. Like, reading took longer to come back online than other things. So you also get this dissociation between different functions.
That's very interesting.
Yeah, that's interesting, because it means that everybody has to remap individually, or these different functions have to do their own remapping. It's not the bit flip, where you can learn to flip the bit. It's like everybody has to go through the pain of all the different functions have to go through the pain of learning what the world is like upside down.
Yeah, and if I recall, that was the kind of point of the Kohler, was that he was trying to figure out what, insofar as there was adaptation, whether it was a kind of single peripheral adaptation or whether it was a more central adaptation. Because you imagine if it's just something like, you know, retina or LGN or whatever adapts, then everyone else gets it for free. Whereas if it's more central, then you could get these dissociations.
Yeah.
There's this interesting relationship between gravity and a field of view, a visual field of view, right? So it's a dangerous illusion for pilots. And if you go online, you see that there's tons of people dying, including one of the Kennedys, that if your vestibular system gets one input, your visual system tilts up or down. So if you sit in an airplane that's accelerating, and all the windows are down because at night it looks like the cockpit is up above you. And then if it's landing, you will see the exact same airplane. Everything is unchanged, but the cockpit now looks like it's below you. So your visual system seems to adjust for the actual angle that the airplane has with respect to gravity. And so it would be really interesting if the visual field flips, if you put the glasses on to then sit in the airplane and do that experiment, whether the visual field tilts up or down.
Mm. Okay.
I have one more question. I know people have to go, but this is for Alex, because I was trying to be ecumenical. And I'm curious about this. So you liked Poincaré's structuralism, which is an interest, and I do feel like a lot of the IIT, I mean, I guess this is really for now as our like standard for IIT as well. You know, one worry about this that I'm sure you're aware of that shows up in a lot of philosophical literature is this worry about inverted spectrum. So the idea is if you've got a representational space and that you really care about is the relationships between the points, then it seems like there are going to be various rotations or transformations that are going to preserve the relations, but flip things around. So it would be possible under that to, you know, have someone that has red and green, or, you know, systematic spectral inversion, but no behavioral consequences. And some people think it's obvious that that can happen, and some people think it's really weird that that can happen. So I'm not sure what an argument it is, but I'm curious to know what you guys think about that from, you know, where you're coming from.
Alex, do you want to answer?
Actually, I'd be curious how you will answer that.
So my opinion is that all these, you know, philosophical thought experiment about the inverted qualia is just too simple, and it won't work in reality. And it won't work if all of our color, you know, qualia is supported by something like, you know, invertible in spectral, you know, orientation and so on. It won't be experienced like as we are doing, probably. That's my conjecture, however. So what I'm saying is my coming from my intuition in sort of a little bit of the mathematics, things can be, you know, symmetric when you're in a really low dimensional, you know, system. Like if you are in a one single line, one dimension, then there are many points that you can flip and then you don't notice anything. And then if you go to, you know, 2 dimension, there is a, you know, that the way to flip and symmetrize becomes slightly more constrained. And then if you go to 3rd dimension, it's even more constrained and so on. And simple concept of color as a 3-dimensional thing, like, you know, hue and saturation and, you know, luminance. I think that's probably the source of this confusion. It is true that, you know, retinal neurons activity or, you know, population neurons can be described in this, you know, 3 sets of, you know, numbers potentially, but our color experience itself is unlikely to be really, you know, purely 3-dimensional. And we had some kind of very interesting color quality symposium. And one of the researchers, Shinya Nishida, told me that, for example, you know, experience of the skin is not possible to reproduce with a, you know, single, you know, number of HSD. And also a brown or orange and things like that only exists in certain kind of, you know, situation, and so forth. So I think, you know, that even the sensation of a relatively simple sensation of a color is super high dimensional kind of, you know, concept that is bound to both space and also many different kind of property around the space, like, potentially related to some kind of emotion. I don't know, this may be not true, but more likely to be related to the texture experience per se. This is supported by the evidence that, color, related neurons in IT or B4 tend to be also, tuned to the shape and also texture as well. So I think in the end, the way we are experiencing the color itself is not close at all to this kind of invertible, spectrum. And if it is like that, it's not like the way we are experiencing. And we are thinking of a way to test this kind of thing. But that requires probably both, large scale psychophysics and also animal experiments of human recording, and also, some kind of theoretical prediction from IIT as well. That's my long shot goal, but my response to you.
I'm tempted to add to that real quick that I wonder if this is only a problem if we operationalize consciousness in terms of behavior, which a lot of these philosophical arguments seem to hinge upon, whereas IIT doesn't do that because it describes consciousness as intrinsic. So there can't be a philosophical zombie because it would be different for the zombie. And to have even just one observer means that the theory is observable. So I know I might be risking everybody, losing everybody here, but I might not be bothered by it as much for that reason, that in the end, it's more important to get at qualia than maybe that there might be more than one possible solution.
So maybe I also want to ask Colin, or maybe also Tom as well, but structuralism or causal structuralism more specifically, like the one that I think is more promising, and also Alex is coming to this side, that is it kind of equivalent in your mind to the representationalism, or is it quite different? And the one potential difference is that, Colin, you said that the problem of the inverted qualia, right? And then leaving aside of that kind of issue, is the structuralism, like the way neurons interact and forms sort of gigantic causal kind of structure corresponds to our experience. Is it almost the same as a representationalism if you adjust your term of or definition of the representation?
Yeah, I mean, look, there are people who call themselves structural representationalists. So I think you should, like, I would think of it as, in the first case as a kind of representationalism, and the more neurally plausible kind of representationalism, at least because it's very easy to see how to get big representational spaces out of a bunch of neurons. Like, I feel like that's the default view. I don't know what you think, Tom, but.
Sorry, what did you say? It's difficult to get representational spaces out of neurons?
No, easy, really easy.
Oh, yeah, very easy. Yeah, I was confused by that. I was like, no.
Yeah, I mean, I assume that's the kind of basis of a lot of your work, right? Is that it's very natural to assume that there's a representational space coming out of here, and you're trying to pick it out. So. Yeah,
but also, I mean, I think it's something I talked about in the talk is like some of these representational spaces aren't really useful or meaningful. Like, I think you can build a representational space like out of all of IT, or you can build it all out of entire V1, but then that assumes some downstream neuron has full access to all the neurons in V1 or all the neurons in IT. So I think from a readout perspective, I think it's pretty easy to think about like early visual cortex, because we just sort of thinking this cascading hierarchy where largely things are connected within regions of the receptive, small or varying size receptive fields. Like, a neuron representing way over here in the periphery is probably not connected to a neuron way over here in the periphery at the next level. It's, they have sort of cones or cones going up and down. In which case you wouldn't really expect, any neuron to have access to all of to a full construction of the V1 representation.
Okay, then maybe, you know, I don't know if you still have time, but, you know, one thing I'm also curious about, you know, what you guys have thought is this, you know, Andrew Horn and Tononi's paper in entropy talks about the space phenomenology. And, you know, they base their argument in terms of, you know, from an IIT perspective, but in that part, you know, we can get rid of. And the simple question is how we experience this, you know, spots of the things, and also its distance or angle or relation of the spots out of something that is completely, for example, you know, disconnected. Or if you are going into the IT and then you are thinking about the readout neurons, are you basically suggesting that when we are saying that, you know, there is this point and this point is far at this particular distance, there is a corresponding readout neuron that is tuned to this particular direction and the distance? Or is it kind of arising from this, you know, structure that, you know, neurons are kind of having this overlapping receptive field? So that's a kind of, you know, question they ask. And I feel, you know, having all these plausible kind of, you know, mechanism to say every time when you ask about the direction or distance or relation, that's so stupid. But it's more parsimonious and also more directly consistent with my own experience, that exponential field and space just is there because of this, you know, structure of the, you know, way that neurons interact and also our consciousness is.
Yeah, the linking of spatial locations, I mean, I think that potentially can be solved. Like if you keep going up the hierarchy, you get larger receptive fields. Like when you think about attention, I'm trying to remember, but like in attention literature, there's like a receptive field of attention, Interrogator and Kavanaugh kind of thing. And they believe that receptive field is because attention is being directed by an area much higher up the hierarchy that has larger receptive fields. And so that area can connect the different locations in space. But because it's so far up and has such large receptive fields, then it doesn't have access to small details at the different locations. So yeah, I guess when you think about it, you know, there does in a way have to be an area that does have access to all that information to make judgments, but it could be 6 stages down the stream through a big process of summation. And then in order to make those judgments, it has to go back down the hierarchy to sort of grab that information. That's very, very speculative, but that would be my view of how it's done.
Yeah, that's good, and also probably potentially also addressable with empirical experiments, right? Like, you know, if your hypothesis would be that, you know, this kind of arbitrary combination of any kind of spots is basically computed by some kind of flexible attentional mechanism that is operating at a higher level. But that also predicts that, you know, if we ask this kind of decision really quickly or simultaneously, then it will interfere with each other because of attentional, you know, limitation or something. But if it's just all there, you know, like Tononi and Horn says, then it won't matter because it doesn't really, you know, depend on attentional mechanism potentially.
Yeah, there's good attentional interference like data. Like, we worked on attentional interference a decade ago, and like when you're doing tracking, and if the dots get too close, they actually zap one another. So you can't track them if they come close to one another, because your attention receptive field is so big. And then what happens is they start suppressing one another because they have, you know, like an excited attention receptive field have excitatory and inhibitory. But once they get close to one another, they start zapping one another, and you can't track them anymore. So I think there's good like evidence for spatial interactions. I wouldn't agree with their sort of view that you can just sort of grab wherever you want without consequence.
The other thing I think this is relevant. I haven't looked at their paper yet, but I just pulled a copy of it that I've been thinking about a lot, and I have a paper on. I mean, so a lot of the stuff, including, you know, so a lot of the work you were talking about, Tom, thinks a lot about linear readouts and linear functions. there's interesting models, and some of this I got from Puget, but this was thinking about some problems in body representation. You can have these things that are quite common in machine learning, where essentially you've got a single representation that's using nonlinear basis functions to bring in the lower level stuff, which then gives you a bunch of simple linear readouts of different features. So you've got one representation that's in a weird space, but it's got nice mathematical properties that you can then do linear readouts off of it for different things. I think that's I think this question, and I think there's a general question about what the bases for consciousness are, in the sense of like the basis functions for consciousness. So you can imagine, I mean, it's weird, but like you get, so sorry, this turns, who is the Olga? Was it Pribram who liked the holographic theories of consciousness? It's a very 70s kind of LSD in the bad way sort of theory. But it's interesting, like if you look at, for example, how JPEGs are represented on the format for JPEGs is not a point, a value at each point. It's a combination of a bunch of discrete cosine transforms, from which you can reconstruct the whole image. And that's got various nice computational properties if what you care about is smoothing and compression. And so the idea might, I do think there's a really interesting question of some of these, of like thinking about not just whether there are representational spaces, but how to think about essentially the axes of that representational space. And given that, my impression is anytime people go and look for actual like nonlinear basis functions in the brain, they're pretty easy to find. So I think there's actually a lot of interesting work to be done there. And then also, presumably that would give you a somewhat different, hopefully like different empirical predictions about what could be distinguished or what could be readily distinguished or something like that. So I've been thinking about that.
About basis functions.
The bases of consciousness, man. We'll talk about this. I'll send you the paper on this because I feel like it's such a great pun that I like it.
I actually have to go, but thank you guys for everything, and hopefully we'll see you guys again soon.
Yeah, I suppose I should probably wrap it up as well.
Thank you, Tom.
Yeah, thank you, everyone. Thanks, Tom. Thanks, Alex. It's a really fun discussion.
Indeed. Thank you, everybody. Bye.
Thank you.